In collaboration with John Rogers at the University of Illinois, we built these devices that are called epidermal electronics, or sometimes also called electronic skin or tattoo electronics. And the idea is that we take standard semiconductor wafers that have all the types of electronic circuits that are inside your iPhone, and we peel them off and mount them onto something that's very flexible and integrates naturally with the skin. For example, the Tegaderm material, which is used all the time in hospitals, or a temporary tattoo. And so with this, we can build technology that can bend very naturally with the skin. It can sense a variety of signals of bodily function, such as electrical rhythms of the body, thermal information, movement, mechanical related information, and optical information. We can integrate this information together, process them on electronic circuits, and then wirelessly transmit the information, all on very small devices that are about the size of a postage stamp and about the thickness of a human hair. We can put these gold sensors that rest right on the surface of the skin, and they adhere very closely to the skin just through the forces of atomic interaction. And with these sensors, this creates a high fidelity connection, low electrical resistance, and so we can begin to pick up some of the electrical rhythms across the body. And so, for example, if we place the sensor near the chest, then we can pick up on rhythms reflective of breathing and reflective of your heartbeat, your so-called EKG. Also, we've recently designed these sensors so that if you mount them onto the surface of your forehead, you can pick up electrical rhythms of the brain, also called EEG. So in short, if you can imagine any sort of electrical rhythm that's typically monitored on the surface of the body, then we can monitor them with our devices. Well, there's a couple of themes that we're pushing our research group, one of which is within the space of perinatal health. And so there, before birth as well as after birth, we've identified some unique applications where we think our technology provides a big value add. Before birth, as you can imagine, pregnant moms needing to wear these big clunky belts to monitor their uterine contractions and their fetal heart rate. Imagine if we could replace that with something that's much less obtrusive, that can pick up the same information. And moreover, within the context of at-risk pregnancies or in situations where we don't have the highest technology, this could be used not only at the hospital, but also at home, transmitting to a smartphone. So that's sort of a space before the baby is born. And then after the baby is born, we're doing some monitoring projects within the context of brain injury. And it turns out this is an increasing value add that we're realizing this is an underserved area of medicine, developing new tools to monitor and understand the function of the injured baby brain in a manner that's very easy to apply and that is very delicate to the sensitive baby skin. And this begins to segue into the other high-level theme that my research group is espousing, which is within the context of neurology. And there, the monitoring the brain injury for babies is one space, but as we can imagine, as one starts to age, equally as relevant is within the context as we age, our ability to respond or to modulate our attention to different new types of inputs will start to slow down. And imagine if we could develop a very simple, quantitative way, easy to apply, on a sticker on the forehead that can provide quantitative outputs of measurements of that. And so we have some paradigms where we can understand mild cognitive impairment. This is done in collaboration with Ricardo Gil da Costa at the Salk Institute. And these same paradigms can simultaneously be useful in understanding the onset of dementia, Alzheimer's disease, but also schizophrenia and also depression.